Okay, let's get started. This was the last slide we covered in um, in our last meeting. As you recall, we started to try to make sense of behavior of systems based on their models. So we started by first order systems where you see these two type of differential equations describing the behavior, or these two types of um, transfer functions. And if you look closely at the transfer function, the standard form where you have KDC in the numerator and T or tau S plus 1 in the denominator, just by having those two values, the two values of KDC or DC gain and T for time constant, you get the shape of the response. You can see how fast the response would react to for example, a unit step input. How long does it take to go through 63% of the change that it's going to go through? And what would be the steady state value of the response once everything is settled? And let me remind you that response of dynamic systems have two parts: the transient portion, which would pass over time, and the steady state, which is what the response will converge to over time eventually. So um, the message there was that by having the model, you can get insight to both transient response, which is the speed of the response, as well as the steady state response, which is the value of the response KDC. If you recall, we looked at a MATLAB tool to get us the response. So let me go ahead and clear this. So there is this website where you can have access to a version of MATLAB, most of the commands, and we looked at the response of a first order system. So just to get started, let me remind you of how to get the response. If you could open this website. The first thing is to define parameters of the system. So KDC, for example, if you say DC gain of this system is 4, which means the ratio of output over input is going to be 4 in steady state, and T time constant is 1 second, which means it's going to take 1 second for the response to go through 63% of its values, or its change rather. Then you need to tell MATLAB what S is. You're saying S is a special variable. I'm going to use S to define my transfer functions. So it's not a ordinary variable, it's the Laplace variable. By saying S is going to be used in transfer function definition. Once you have that, then you can define your transfer function. Let's call it G1 as KDC, the standard form, over T times S plus 1. So I use the asterisk to show the multiplication, and then you can look at the step response. So you can type step of, and if u is something other than 1, you need to define it. If the value of input is anything other than unit step, you need to define it. So if u, for example, value of input is 2, you need to define it, and then step would be step of u times g1, which is how we define our transfer function. And if you hit enter, it goes through the calculations and it will plot this response for you. So this is the response of a system with KDC of 4. So so that's the amplification factor. So if the level of input is 2, you know the steady state response would be 2 times 4, which is 8, as you can see from the plot. Time constant is 1 second, so it means in 1 second the system goes through 63% of the change that it's going to go through. So 63% of 8 is 4.8 roughly. So at 1 second you are at that value of response. Now, another interesting plot you can generate is you can compare response of systems with different values of time constants or different values of DC gain. So how can you do that? If you hit up arrow, you bring the last command that you executed. So this time, what you can do is you can put this command after plotting step. The command is hold on, which means plot the next plot on the previous plot. If you put hold on, basically it's going to plot the next plot on the previous figure so you can compare. So if you have this hold on command and then go ahead and change something in your transfer function. For example, you can say, I want the time constant to be, instead of 1 second, be 2 seconds. So it's going to be a slower system. And then you need to define the transfer function. If you're not changing KDC, you don't have to redefine KDC. It's already in the memory. So you can say G2 is the same KDC divided by now the new value of t times s plus 1. And then you want to step U and G2 on the same plot, basically. So if we did this correctly, you get another plot exactly on the same figure that we already have. And you can compare the response of these two systems. Again, the steady state response is the same because KDC is the same for both systems, but one is twice faster than the other one. The time constant for the first system was 1 second. So in 1 second, it reaches 80% of the final or steady state response. I'm sorry, 63% rather. So which is roughly close to 5. So in 1 second, it gets to 5. The other system takes 2 seconds to get to the exact same value. So you can play with this and get various responses. The other thing you can do, for example, because hold is on, you don't have to execute the previous commands again. What you can do is you can look at the effect of changing KDC. Yes, sir.
Can you minimize that thing where it says one use scripts?
Yeah, so you can see the rest. Yeah, thank you. Yeah, so you can see the entire thing. Thank you. So the other thing you can, for example, do is you can change KDC. If KDC instead of 4 was 1, if KDC instead of 4 was 1, and t remains the last value which we defined, which is 2, then you can define a third system as transfer function of KDC divided by t times s plus 1. And then look at step of u times g3. What do you expect the response to look like? How would the response be different? Yes? So the steady state would be at 2 instead of at 8 because KDC is 1. So let's give it a try. So you can see that the response is now settling at 2, and it's now 63% of 2 is roughly 1.2, which is here. So you can see the time constant is 2. So if you're given a plot like this, and you're dealing with a first order system, you can simply look at this plot and determine value of KDC and value of time constant, which essentially gives you the transfer function. So you can look at the response and find the model of the system. Can you see that? So you can look at the response and find the model. Yes?
Can you refresh my memory on what KDC is again?
Yeah. KDC is, if you look at this slide, I think it's, so if you look at this slide, KDC is the numerator of the transfer function once you have the transfer function in the standard form. And the standard form is when you have a constant times plus 1. That plus 1 makes it the standard form. So KDC, therefore, would be value of the response. If you have a unit step input, if U is 1, KDC would be the steady state value of the response. Or it would be, so what if U is not 1? What if U is 2? KDC's role would be to show you how the input would be amplified to get the steady state output. And is T clear, the time constant? So by looking at the response, you can basically calculate the value or determine the value of KDC and tau. So I think one of the questions of the sample exam was around this idea. So you were given a plot or multiple of plots, and you were asked, what is the time constant of this system, or what is the time constant of the other system? Or you can be given the model and be asked to plot the response or compare the response. And the other point I made towards the end of last class was it really doesn't matter what kind of response you're looking at or what you're trying to calculate. If you look at the impulse response of the exact same system, impulse response is equivalent to giving the system some initial condition and let it freely move. Even in that case, the time constant would determine how fast the system would react. So if you, for example, hold on to the previous plot and look at the impulse, there is a command called impulse response of the last system that we defined, which is G3. Let's see how it will. So you can see that in the impulse system, the effect of impulse is immediately gives the system some initial value of response, initial condition. So it starts at 1 and it goes towards 0 in steady state, but these behave exactly the same way, with the same trend. So it takes 2 seconds to go through 63% of response, either if you're looking at the step response or if you're looking at the impulse response. The 63% of change would be going from 1 to 0. So 63% would be when you go down by 0.63. When you go down by 0.63, you are roughly at 4. So that's exactly what you have. So again, you could be given the impulse response, and again, you can calculate the time constant of the system. So that was the review of what we did for first order systems, and we finished by looking at the Bode plot. The Bode plot basically shows you how the system reacts to sinusoidal type input. So it shows how the ratio of output over input is a function of frequency, and how the phase shift is function of frequency. And the fact is, they're both function of frequency, so each system has a special frequency at which this rolling off starts happening, and at which the sharp change in angle is centered. So that's another behavior of a first order system that again you can use to get information about the actual system and its model. Now let's move on to second order systems and apply the same concept now, this time to second order systems. A second order system, for example, could be the model of a mass spring damper system. We have seen electrical systems that are second order systems. And it's a common practice to take this my double dot by dot plus ky, this differential equation, and take it into a standard form. What is the standard form of the differential equation? The standard form is when the coefficient of double dot is 1. So when the coefficient of double dot is 1, in the case of mass damper spring, you will get 2 zeta omega n as coefficient of y dot and omega n squared as coefficient of y. And what is multiplied by ft would be kdc times omega n squared. And either from the differential equation or from the transfer function that follows from the differential equation, you can calculate the DC value of response. So let's go ahead and warm up with calculating the DC value of the response. So my question to you guys is going to be, if I know my u of, instead of u, let's go with the first form, which is this equation 1. So if I know my f of t is 1, so I'm applying 1 newtons, a constant level of force to this system, what is going to be my y steady state? What is the steady state value of displacement? So I have a mass attached to a spring and a damper in parallel, and I'm pulling on it with a constant level of force. I'm asking you, how much would the mass move in steady state? And your answer is? 1 over k. And how did you calculate that?
Just set any time differentiated.
Set any, exactly, very good. So set any variable that is a time differential to 0. So which means y double dot and y dot has both, they have both to be equal to 0, which means k times y steady state is equal to f of t, which in this case is 1. So that gives you y steady state of 1 over k, where k is stiffness of the spring. So it's only the spring that defines the value of steady state displacement. Neither mass nor damping have any effect on the steady state value of the response. And by the way, you can get the exact same information from this transfer function. We talked about final value theorem. Now, we didn't explain in detail what final value theorem was, but essentially, if you get the transfer function g and set 0 for s, so calculate g of 0 instead of g of s, you will get your steady state value of response. This is going to be equal to y steady state. And try this. Set s equal to 0, 1 here, 0 plus k, so it becomes 1 over k. And that makes sense. You know why? Because didn't any time differential give us a power of s? Do you remember? So y dot gave us s. Y double dot gave us s squared. So setting powers of s is equivalent to setting time differentials equal to 0. So that's why you get exactly the same steady state response. So far we know how to find steady state response of second order systems. Let's now see if we can get more information. So this is the steady state response. Let's see if we can get more information about the transient portion of the response, how the system will behave until it gets to the steady state response. So we talked about the DC gain, which is 1 over k. And you know from your course in vibration that zeta, when you take your ordinary differential equation and turn it into the standard form, the coefficient of y dot would be 2 zeta times omega n, and the coefficient of y would be omega n squared. So omega n is natural frequency. It has a significant meaning when it comes to frequency response of systems. And zeta is what is called damping ratio. So we'll see damping ratio and natural frequency will both play significant roles in the transient portion of the response. Now, we didn't see any trace of them in the steady state response. The only thing that affected steady state response was stiffness of the spring. But when it comes to the transient portion, you can see that both natural frequency and damping ratio would play a role. So let's start by talking about time constant of a second order system. If you know that the time constant of a second order system is 1 over zeta omega n. 1 over zeta omega n, where zeta is damping ratio and omega n is natural frequency, it should start becoming clear why both zeta and omega n are going to affect the transient portion of the response. Because time constant essentially defines a significant and an important property of the response. It essentially defines the speed of response. So knowing that time constant is 1 over zeta omega n, as zeta goes up, would the system become faster or slower? Let me repeat my question. We know time constant of a second order system is equal to 1 over zeta times omega n. So both zeta and omega n are in the denominator of the time constant. So as zeta goes up, would the system get faster or slower? So zeta goes up, which means denominator goes up, which means the ratio goes down. As the time constant goes down, the system is faster. So it takes less time to go through a certain percentage of response, which is similar to what we defined. So keep that in mind. So let's see what else we can learn about this second order transfer function. Okay. The way that we start from 1 over m s squared plus bs plus k, this comes from the differential equation. Now, the way to get from this to this standard form, where coefficient of s squared is 1, is simply by dividing everything by m. So if you divide everything by m, you get rid of coefficient of s squared, and here you have b over m, here you have k over m. So when you divide this portion by m, you have also to divide numerator by m to keep the same ratio. Now it's easy to see that m will drop from here. B over m will be 2 zeta omega n, and k over m is omega n squared by definition. And here you have 1 over m, which would be your kdc times omega n. And it should be clear why, because when you set s equal to 0, the first two terms of the denominator will go away. Omega n and omega n will cancel each other, so what is left is kdc, which we know is equal to 1 over k in our case. Now, if you recall, last time we introduced the concept of pole of a transfer function. What is the pole of a transfer function? Hint, poles and zeros both are values of s. So values of s that will make the denominator of a transfer function go to 0 are called poles. And I will highlight the importance of poles in determining the transient response of system. So let's start by finding poles of this system from this standard form. So what I'm asking you to do is to set s squared plus 2 zeta omega n s plus omega n squared equals 0, and find values of s that will make this equation true. So what values of s will make the denominator of this transfer function equal to 0? So it's a quadratic polynomial. You need to use quadratic formula and find those values of s. So there will be two of them. So s1 and 2 are going to be, so in quadratic formula, the coefficient of s is a, coefficient of, rather s squared is a, coefficient of s is b, and the last portion is c. So the formula calls for minus b. So minus 2 zeta omega n minus b plus minus square root of b squared, which would be 4 zeta squared omega n squared minus 4a times c. A is 1 and c is omega n squared. So minus 4 omega n squared divided by 2a. The whole thing is divided by 2a. A is 1, so it's divided by 2. So that's the quadratic formula for finding roots of a polynomial. What values will make the polynomial go to 0? Is this correct? Is it minus b plus minus square root of b squared minus 4ac divided by 2a? Is that the formula? For those of you who memorized it. Okay. So that's the coefficient. So that's the formula. Now you can simplify that. So for example, it's easy to see that 2 and 2 will simplify here. And also you can factor 4 out of this square root and simplify it with 2. So, so 2 will go away. So what you will be left with is going to be minus zeta omega n plus minus. And if you look closely, omega n squared is repeated. So what you can do is factor omega n squared out. So you can bring omega n out, and this becomes square root of, what is left? Zeta squared minus 1. So these are the two values of s that would make the denominator go to 0. So depending on what value we have for zeta and what value we have for omega n, these two values of s will make the denominator go to 0. Now, if I switch the place of zeta squared and 1, what am I doing? I'm basically factoring a negative 1 out. So let's try this. So if we factor, so if we do that, so if we say this is equal to minus 1 minus zeta squared. Can you see that? Oh. Can you see that zeta squared minus 1 is equal to minus 1 minus zeta squared? You basically are factoring a negative 1 out. Now, what is square root of negative 1? I or j, both are used. So we are going to use j here. So it's equal to j. So basically this tells you that s1 and 2, the two roots of the denominator of this transfer function, are going to be minus zeta omega n plus minus j omega n square root of 1 minus zeta squared. So we took the negative 1 out. Why do we do that? Why do we rearrange zeta squared minus 1? Because in majority of cases, zeta is going to be less than 1. Majority of physical systems would have a zeta that is less than 1. So in order to be able to calculate a number from the square root, we'll rearrange it so the number under the square root is always a positive number. So we can find square roots. We don't have to deal with complex numbers. So we take the complex number, which is square root of negative 1j, out, basically, which is a purely imaginary number, by the way. And you can see on this slide, depending on the value that zeta will assume, the system would be either called an underdamped system, if zeta is between 0 and 1, or an overdamped system, if zeta is more than 1, or critically damped system is if zeta is exactly equal to 1, or undamped system if zeta is exactly equal to 0. Why are we looking at this? I'm trying to convey this message, that the location of poles would have a significant impact on the transient response of dynamic systems. So take this down, please. So location of poles define the transient So the location of poles will define the transient response. And do you see that as value of zeta changes, the location of poles also change? See, this S1 and S2 will become a number depending on what value zeta assumes and what value omega n will assume. If zeta is, so let's start by looking at each of these cases one at a time. So if zeta is less than 1 and we are dealing with an underdamped system, so if zeta is less than 1 and we are dealing with an underdamped system, it's easy to see that omega n is going to always be a positive number. Natural frequency is going to always be a positive number. Zeta is also a positive number less than 1. So you can see that this portion of the pole is going to be a negative number. Can you see that? Minus zeta omega n is going to be a negative number. What else do you see? The fact that zeta is less than 1 will give you a positive number under the square root. So square root of a real number is a real number. But look, here this is multiplied by j. So both poles are going to be a pair of complex conjugate numbers. What does a complex conjugate number mean? So imagine that our omega n is 10. So if omega n is 10 and zeta is 0.2, S1 and 2 will become what? So minus 0.2 times 10 plus minus j times 10 times square root of 1 minus 0.2 squared. So we are dealing with a specific case where zeta is 0.2, and omega n is 10. By the way, what is the unit of omega n? Radians per second. Yes. So unit of natural frequency is radians per second. What is the unit for zeta? It doesn't have a unit. It's dimensionless. Yes, very good. So it's a ratio. It's damping ratio. Yes.
So for an underdamped system,
Mhm.
zeta is going to be less than 1, but is it always going to be greater than 0?
Yeah, because the case of 0 has a different name. It's called undamped.
Okay.
No damping. So it's between 0 and 1. Not equal to 0, not equal to 1. Greater than 0, less than 1.
Okay.
Good question. Thank you. Okay. So if for this specific case, where are these two poles located? So 10 times 0.2 is negative 2. So negative 2. So plus minus. So if you calculate SQRT of 1 minus 0.22 power 2, you get roughly 0.98. So plus minus 0.98 times j. And this is multiplied by 10. So this also should be multiplied by 10, which gives it, so moves the decimal between the two. So this instead of 0.98 becomes 9.8. Plus minus 9.8j. Okay? So if you put these 2 points on the complex plane, this is the figure you get. So this is the real axis. So the horizontal axis is reserved for real numbers, and the vertical axis is reversed for purely imaginary numbers. So these two poles are located at negative 2. So this is negative 2. You can see right here. So this is negative 2. plus minus 9.8j. So this is plus 9.8j. So this is plus 9.8j. And this is minus 9.8j. And as you know, we have two poles. So these are the two poles. So what do we see here? We see when we have an underdamped system, the two poles are a pair of complex conjugate with a negative real part. So the real part is negative. So a pair of complex conjugate numbers, negative real part. And remember, the time constant was what? Time constant was 1 over zeta omega n. And guess what? The real part of the two poles, is located at negative zeta omega n. So if you know where the two poles are located, you immediately have your time constant of the system. So what is the time constant of this system? This specific example that we have. What is the time constant? In order to calculate time constant, we need to know what zeta times omega n is. What is zeta times omega n for this system? Did I hear 2? You're absolutely correct. So this is 2. So minus zeta omega n is 2. So the time constant is 1/2 seconds. So the time constant for this system is 1/2 second. With the information that you're given, can you calculate the steady state response? What information are you given? You're given zeta and omega n. Do you have everything you need to calculate the steady state response? What was the steady state response equal to for a second order system? 1 over k. So do you have 1 over k? So zeta is what? So omega n is square root of k over m. So when I gave you omega n, I gave you the square root of ratio of k over m. So you don't know what k is or what m is, but you know the ratio. And what is zeta? Do you know what zeta is in terms of these? Let's calculate it once so we always know what zeta is. Now, I told you in order to get from this form of the transfer function to the standard form, you divide this by zeta, which means if you look closely here, b will be divided by m. So d divided by m is going to be equal to 2 zeta omega n. That's the equation that you need to always keep in mind. Now we know what omega n is. Omega n is the square root of k over m. So from here you can calculate. So this is there. In other words, it's equal to 2 zeta square root of k over m. So can you tell me what then zeta is equal to? So in order to calculate zeta, you need to take this. So b over m is equal to 2 zeta square root of k over m. In order to single zeta out, you need to divide both sides by 2. And you need to multiply both sides by inverse of square root of k over m to get rid of square root of k over m. So zeta, therefore, is b divided by 2 over square root of k times m. So zeta is equal to b over square root of k times m. So if I'm giving you zeta, I'm basically giving you this ratio of b over 2 square root of k over m. So you have three unknowns, b, k, and m, and two equations. So you don't know. You can't calculate b, k, or m from two equations. So the bottom line is you don't know what the steady state response is unless I gave you a third piece of information, either giving you m or giving you stiffness or giving you b value of damping. If you have that third piece, then you can plug it into these two equations and figure out what k is. So we don't know what k is. Now, I'm going to show you in MATLAB how to create these two plots. One of them is called the pole zero map. So this is the pole zero map. If you look closely here, this is the title of the plot. So it shows you on a single plot the location of poles of the system in addition to location of zeros. This system, does it have a zero? This transfer function. Zeros are what? Zeros are values of s that will make the numerator go to 0. Does it have any zeros? Any value of s will make the numerator go to 0? Look at the transfer function. Do you see any s in the numerator? So there is no value of s that will make the numerator go to 0, which means this system has no zeros, but it has two poles. Okay, so let's go ahead and fire up MATLAB. And I'm going to resize it so I can see the numbers. Okay. So I'm reconnecting to the server. So I'm going to clear my space by typing CLC. It clears your space. So I'm going to define KDC as 1. So this system has a steady state DC gain of 1. Omega n, in my case, is going to be 10 radians per second. And zeta is going to be 0.2, which clearly makes it an underdamped system. It's between 0 and 1. Again, we need to tell MATLAB that s is a special number, is a special variable rather. And then we can define our transfer function. So the standard transfer function is k dc times omega n in the numerator to power 2 divided by, in the denominator we have s to power 2 plus 2 times omega n times zeta plus times s rather, times s plus omega n squared. This is our transfer function. So let's go ahead and execute this up to this point. So you see the transfer function given to you. So omega n is 10. So squared of that omega n squared is 100. KDC is 1. So 1 times 100 is the numerator of the transfer function, as you can see. The denominator is s squared times 2 zeta omega n. Zeta is 0.2. So 2 times 0.2 is 0.4 times 10 is 4 plus omega n squared, which is 100. So you can check that the transfer function is what we expect. The next thing you can do is you can look at poles of this transfer function. And you can even better plot them on a plot called pole zero map. So PZ map of the transfer function gives you this plot. So this is a complex plane. The horizontal axis is the real axis. This is the horizontal and real axis. This is the imaginary axis. We don't see the imaginary axis, but basically going up and down, you go up and down in the imaginary axis. So as we calculated in our hand calculations, we know that the two poles are located at plus and minus 2 plus minus 10j or close to 10j. And you can see the two poles are located, this is the real axis, negative 2 plus minus 10j. So you know, as soon as you see this, even if you did not have any clue what system this was, if you were only given the pole zero map, you would immediately conclude that you're dealing with an underdamped system. Why? Because for any and every underdamped system, you have a pair of complex conjugate poles with a negative real part, and that's exactly that case. So negative real part, a pair of complex conjugate. Complex conjugate means plus minus a constant times j. And you can then look at the response of this system. So you can type step G1. So you can look at the step response. And as you expect from an underdamped system, it starts from the initial condition of 0, goes through oscillations, and eventually settles at KDC. KDC, we defined it to be 1, so it settles at 1. Okay? Now, what have we shown so far? We have shown the effect of zeta in determining the transient portion of the response. So if zeta is between 0 and 1, this is the type of transient that we have. And more importantly, we talked about the speed of response. We said time constant is determined by zeta times omega n. In this case, zeta times omega n is what? What was zeta times omega n? We calculated to be 2, which meant our time constant is half a second. So in half a second, we get to a critical portion of response, and we'll talk about it as we go forward. What if zeta wasn't what was the value? 0.2. What was 0.8? Is this system still underdamped? Okay. But would the transient response look differently? Do you expect it to be faster or slower? So zeta goes from 0.2 to 0.8, which means the denominator gets larger, which means the t gets smaller, which means the system gets faster. So let's quickly test this. So let's go here and define zeta instead of 0.2 to be 0.4. So let's try that. The first thing to see is the PZ map. You can see the PZ map. Now the real part of the pair of complex conjugate has changed. Instead of zeta minus zeta omega n, which defines the real part being minus 2, it's now minus 4. So the two poles have shifted towards left. So the two poles have moved toward left. The real part is negative and a larger negative number, or larger in absolute value, but a smaller number. Now let's look at the step response. So step response shows a faster response. Not only that, but also a smaller overshoot and faster settling, essentially. Let's see if we can put these two plots next to each other. So let's try this. So we are going to call this G2, the one that has zeta of 0.2, and call zeta of 0.4 is what we call G2, and zeta of 0.2 we are going to call G1. So we have two different transfer functions. You can see one transfer function has a different value of zeta omega n because zeta is different. So let's plot them next to each other. So g1 comma g2. So we can use the step function when you're plotting step response of two systems or more than two systems. Each transfer function should be separated by a comma. So g1 has zeta of 0.2 and g2 has zeta of 0.4. Let's look at the response. Can you see the effect of zeta? So you can see that G2, the system with higher damping, is a faster system in the sense that its response settles faster. It gets to steady state faster than the previous system. Okay? So we talked about effect of zeta. So as you increase zeta, the two poles move farther and farther left, and the system gets faster and faster as you expect from the definition of the time constant. Should we write this down somewhere? So as zeta goes up, the two poles move to the left. So as zeta goes up, the poles move to the left, and the system becomes faster. And remember, the imaginary part also changed in location. See, plus minus j times omega n squared root of 1 minus zeta squared. So by changing zeta, the imaginary part also changed in its location, and we'll talk about it in more details in a future slide. So that was what kind of system? Underdamped, and zeta is between 0 and 1. So we established some trends for the transient response of underdamped system. So let's move forward. And this time, look at the settling time. We talked about settling time and its importance. The most common form of settling time is settling to 2%. This is the most common. So 2% of the steady state response. And it's roughly 3.9 to be exact. So it's 4 times the time constant of system. So if the system has a time constant of 2 seconds, like the example we had, it takes 4 times that, which is 8 seconds, for the system to reach to 2% neighborhood of the steady state response. So what do we mean by that? So if you look here, this is the steady state response, which is 1. 2% neighborhood is 2% to 1, which is 0.98. So it basically tells you that it takes 8 seconds, 4 times half a second, so 2 seconds rather, to get to that vicinity. So this 2 seconds, so this 2 seconds is settling time, which is 3.9 times time constant. So this is the 2% neighborhood. So if you follow along, you see that. So that's another important information that you can determine simply by knowing either the location of poles or by knowing the transfer function, so you can calculate the location of poles. And this settling time has a general formula. So it's minus natural log of the tolerance fraction, 2%, 10%, 5%, whatever that tolerance is, divided by omega n times zeta, which is your time constant. So this 3.9 or 3 or 2.3 comes from this negative natural log. You can also calculate the rise time, how quickly the system initially jumps up. And the rise time is roughly 2.2 times the time constant. So rise time is roughly 2.2 times the time constant. Time constant is 1 over zeta omega n. So you can talk about the rise time. Again, our system, the previous system that we investigated, had a time constant of a half a second. So half of 2.2 is 1.1 second. So if you look back at this, so going from 10%, which is 0.1, to 90%, which is 0.9. So this is going to be the rise time. The difference between 10 per second or 90%. So this is so this number, which is is supposed to be 1.1, is not quite what we get from the plot. So we'll look into that. But the definition of rise time is the time that it takes to go from 10%, which is 0.1, to 90%, which is 0.9. So it basically captures this initial jump. So settling time captures how long does it take to settle, but rise captures how quickly the system jumps up. And also percentage overshoot, how much this initial overshoot of the system is, also related to damping ratio of the system. So the higher the damping, the lower the percentage overshoot. So there is an equation of e to power minus zeta times pi over square root of 1 minus zeta squared. So by knowing zeta, you can calculate percentage overshoot. Or there's another formula that is natural log. So if you know what percentage overshoot the system has, if you have the response. So let's go back here. What is percentage overshoot of this system roughly? So if this is roughly 0.5, so let's make it easy. This is 50% overshoot. So steady state value is 1, so it goes over that value by 50%. So bring out your calculators and plug 50% into this equation. So that's 50% divided by 100. So 50 divided by 100 is 0.5 rather. So minus natural log of 0.5 over square root of pi squared plus natural log of 0.5. So this is the formula. So it's natural log of 0.5, which is 50%, over square root of pi squared plus natural log of pi. Did I use the formula correctly? Am I missing anything? So minus on the top, plus at the bottom, and there's a squared. Oh, okay, so the second part has a square. So let me take it to power 2. So this needs to be taken to power 2. See, the damping ratio that we calculate is very close to the actual damping ratio. So the damping ratio of the system was 0.2. And remember, we rounded percentage overshoot. So percentage overshoot is not quite 50%. So look, if you look at the plot, the percentage overshoot is less than 50%. So if you make an exact measurement and plug into this equation, you get the damping ratio. So the bottom line is, if you have the response, you can calculate many of the important constants or properties of the model. Or if you have the pole zero map, if you know the location of poles, you can get a lot of that figured out based on the strong relationship between location of poles and the transient portion of the response. So let's move on. We discussed in details about the behavior of an underdamped system, the transient response, the steady state response. Let's move on to now an overdamped system. So the question is, where would the two poles of an overdamped system be located? So what do we know about an overdamped system? What has to be true for a system to be overdamped? Let me ask the gentleman sitting at the very back. How an overdamped system is characterized? Absolutely. That's the only defining factor. So if zeta is more than 1, look at the equation that gives you the two poles of the system, which says SP, which basically gives you the location for S1 and 2. If zeta is more than 1, what can you tell about that? The value of the two poles. Where are they located? Look at the equation. You need to be looking at the equation. If zeta is more than 1, what will be clear? If zeta is more than 1, what can you say about this? That would be negative. So you have an imaginary number. But remember, you already have a j there. So that j and the j resulting from that become negative, cancel each other. So the result is that you have two poles that are not imaginary, which means they are both real numbers. Do you see the difference? Underdamped had a pair of complex conjugate poles. So there was an imaginary part. For overdamped, there is no imaginary part. They're two poles, they're distinct, but they're both real. So let's go ahead and look at an example. So if zeta, for example, is 1.2, which is clearly more than 1, and the same natural frequency as before, natural frequency of 10, you can see that the system would have two poles. They're both real and negative. You can see this is the real axis. So one pole is close to -6, the other one is close to -19. So the two poles, negative but both real. That's what you get from the PZ map. And if you look at the step response, now this is the step response that you expect to have. There is no overshoot, no oscillation, and it looks very much like the behavior of what type of system? Very much look like first order systems. Do you see that? First order system didn't show any oscillations. It was just an exponential rise and settling at a steady state. Now, again, the steady state response is 1 over k. The steady state response is 1 over k, but the location of poles would determine that we have an overdamped system. Okay, so we talked about the overdamped system and the fact that the transient portion has no oscillation. Now, let's move to another special case, critically damped system. What has to be true for a critically damped system? What is a critically damped system? What is the value of zeta? Zeta is exactly equal to 1. Now, look at the location of two poles. If zeta is exactly equal to 1, what will happen?
You'll only have one pole.
you have only one pole. But this is a second order system, so it has to have two poles. So what can we say? The system has two poles, but they're both located at the same place. So you have a pair of repeated poles. So you have two poles, but they're located at minus zeta omega n. So repeated poles. It's still two poles. Okay. So let's look at the example again one more time. Again, natural frequency is exactly the same. DC gain is exactly the same, equal to 1. If you set zeta equal to 1 and look at your pole 0 map, you can see only one asterisk on a pole 0 map, even though it's a second order system, but the two poles are exactly on top of each other. And as you expect, the response, again, has no oscillations, no overshoot. It simply rises up and settles at the steady state value, which is determined by KDC, which is 1. This is the step response. And the time constant, again, is 1 over zeta omega n. So 1/10 of a second is the time constant of the system. What is left? What haven't we talked about in the four possible cases? The very last possibility is when zeta is exactly equal to 0. Now again, look at this portion where zeta is present. If zeta is exactly equal to 0, what can you say about the two poles? What kind of numbers are they going to be? Also look here. So if zeta is exactly equal to 0, what will definitely go to 0 from the definition of two poles? Remember, this was the real part, and this was the imaginary part. So if we are dealing with an undamped system, what portion of the two poles is exactly equal to 0? The real part. Which means you have two poles that are what? Two poles that are imaginary. So the real part of the two poles are equal to 0. Look at the pole 0 map. This is the real axis. So the real axis shows that the real part of both poles is exactly equal to 0. So one pole located here, one on the top. So if you are given a pole 0 map and two poles are on the imaginary axis, you're dealing with an undamped system, no damping. And if you look at the step response, this is the typical undamped response. So it's pure oscillation. So it just keeps repeating the response without any energy loss. So zeta being equal to 0 means what is the value of damping? 0. An undamped system means there is no energy dissipation, no damper. That's why the system will basically oscillate forever. So this was all the time response. How about the frequency response? The distinct behavior of frequency response of second order systems again can be found with a Bode plot, where on the top you have the ratio of output over input in steady state, and the bottom you have the phase shift. Now for all second order systems, you go through a 180-degree phase lag. So you go from 0 phase lag to 180-degree phase lag, and it happens at the natural frequency. The switch, this frequency is the natural frequency of the system. And when you have an undamped system, you have a significantly large value of ratio of output over input. So there is no attenuation, basically. So if you are exciting the system exactly at its natural frequency, you're entering resonance, which theoretically you go to infinite amplitude. So it means destruction of the system, not necessarily infinite amount of motion, but an unacceptable level of motion. So that defines, so this is the resonance. So this is natural frequency, and this is resonance. this is, it's hard to see. In the written notes, it's easier to see. This is the undamped system. So if there is no damping, the output over input is a significantly large number. Now, as you increase damping, this peak goes down. So this is underdamped, then critically damped, and then overdamped. So the 4 cases basically brings the ratio down. And the 4 cases of zeta also define the pattern of change of phase. So we're not going to discuss much more than this in frequency domain. This plot should help if you want to etch something on your brain in this class, and then if you want forget right after this, this should be this plot. The equation that we had, what was the equation? The equation was this. Then S1 and 2, the two values of S was, the two poles of the second order system was minus zeta omega n plus minus j omega n square root of 1 minus zeta squared. In general, you can show the two poles on this complex plane. So you can see this is minus zeta omega n. This is the real part. And these are the imaginary part is plus j omega n square root of 1 minus zeta squared and minus j omega n square root of 1 minus zeta squared. So that's exactly the formula we have. Now, if you look at the geometry, you can determine a few important factors from this figure. Now, this is a right triangle, and you're looking at the hypotenuse here. So if you take into the account that this is j omega n square root of 1 minus zeta squared, and the fact that this side is minus zeta omega n squared, and apply Pythagorean theorem, you can see that this distance is going to be your natural frequency. Why don't you go ahead and apply it? So whatever this length is it's squared is equal to squared of this plus squared of that. So so squared of this would be zeta squared omega n squared. Squared of the other one would be omega n squared. J simply will turn into a negative 1. So let me turn that into. So omega n squared, and this becomes 1 minus zeta squared. So square root of this, which is Pythagorean theorem. So you can see zeta squared omega n squared would be cancelled by zeta n omega n squared. So what is left is omega n. So this distance essentially is omega n. So if you're given the location of the two poles, you can calculate omega n. But you can also calculate zeta. You can also calculate damping ratio. Again, by knowing the fact that, so if you look at this angle, for example, or this angle. I like looking at this angle instead of the other angle. So if you look this angle beta, what is sine of beta? Can you tell me? This is the, yes, sir. Yes.
That'd be negative in your square root. That'd be negative omega n.
Because the j factor? No, this is a good point. I misspoke when I said because it's j there and it becomes negative 1. This is indicating that it's imaginary. But when you apply the theorem, this is a number, and so this is a number. So the two sides are real numbers. They're not imaginary numbers. That's why you don't need a negative. So when you apply the theorem, it's a triangle. So sides of triangle are not imaginary number. It is on the complex plane, j is there to tell you this is the imaginary part. But when you look at the size, the two sides, they're real numbers. So that's why you don't need a negative. Very good question, though. Now, this is a right triangle. What is sine of beta? Sine of beta is this side, which is what? This side is zeta omega n dividing by this length, which is omega. So what is sine of beta equal to? It's equal to zeta. So again, if you know the location of two poles and you calculate sine of the angle between the positive imaginary and the ray connecting the location of one of the poles to the origin, you can calculate your zeta. Or in other words, you can say inverse sine of this angle is equal to zeta. And this plot is probably the most interesting plot. The fact that sine of that angle defines zeta tells you when you're exactly on the imaginary axis, what is the angle? This angle, the angle that is between the location of the two poles and the imaginary axis. When the two poles are exactly on the imaginary axis, what is the angle? Angle beta is exactly 0. Isn't sine of beta also equal to 0? So when you're exactly on the imaginary axis, zeta is equal to 0. And wait a second, this case was here. When you had an undamped system, both of the poles were on the imaginary axis. So that confirms that when you have the two poles exactly on the imaginary axis, you're dealing with no damping, 0 damping. Now, as this angle increases, you're going from value of zeta towards value of zeta exactly equal to 1. You remember when we had critically damped system, we had two poles exactly on top of each other, as if they looked to be one pole. Let me show you the critically damped system one more time. The critically damped system only had one pole, but in reality, there were two poles on top of each other, and it was on the real axis. On the real axis. So this figure tells you that as zeta increases, now each of these points is a different system. It's not that this shows behavior of one system. It basically captures all possibilities for a second order system into one plot. So you're going from undamped system, as you increase damping, you eventually arrive at damping of exactly equal to 1, and the two poles would meet each other and would be on top of each other. Located at minus zeta omega n, zeta is 1, so they located at minus omega n. And by the way, isn't this length omega n? So as zeta changes for a system that keeps the same omega n, the two poles move on a semicircle. All the way from imaginary axis for zeta of 0 to real axis for zeta of exactly equal to 1. And if you assume any position in the middle, you know definitely you are dealing with an underdamped system. So zeta is neither 0 nor is it 1, so it's between 0 and 1. So that angle, again, is associated with value of zeta. And what happens if zeta goes more than 1? Then you have two poles, that one is located on this side and the other one is located on that side. So these two poles belong to an overdamped system. So please come back to these figures repeatedly. I could ask you multiple questions. I can give you a pair of poles and ask you to calculate natural frequency and damping ratio. Can you do that? Let me try you. So I'm going to give you a pair of poles. I'm going to say we are dealing with a second order system where S1 and 2 are minus 1 plus minus 2j. Tell me what zeta is and what omega n is. So let's start by omega n. What is omega n? Omega n is going to be a square root of 1 squared plus 2 squared. Now, negative 1 is here, 2 is here. So if you take 1 squared and 2 squared, you get squared of this. So it is going to be square root of 5 radians per second. That's your natural frequency. Do you agree? So for omega n, so if you look at this triangle, so I got it from this triangle. So this is omega n, this is the real part, and this is the imaginary part. So my imaginary part was 2, my real part was 1, so 1 squared plus 2 squared square root gives me omega. So I have omega n, can I calculate my zeta? What is zeta equal to? Zeta is equal to sine of beta. So I need to calculate sine of beta. So sine of beta is what? Is what is facing beta, which is what? The real part is 1. So it's 1 over what? Over omega n, which is square root of 5. So zeta is 1 over square root of 5, whatever that number is. And it's definitely less than 1, so we're dealing with an overdamped system. What other question can I ask you? The other question I can ask you is this. I can give you a pole zero map. I can give you the real axis. So let's say this is the real axis, this is the imaginary axis. So real axis, real, and imaginary. So I can give you this, and then give you various points on this, and ask you, what kind of system is this? So for example, I can give you these 2 poles, either with exact location or without exact location, and ask you, what kind of system is this? What kind of system is this? Where you have a pair of complex conjugate. If you have to go through your notes, please go through your notes. You have a pair of complex conjugate with negative real part. What kind of system is that? Underdamped. If I told you this is a second order system, but I gave you 2 poles that are on top of each other. So let me change colors. So blue is underdamped. If I gave you 2 poles that were exactly on top of each other somewhere here, and I ask you, what kind of system is that? Or not what kind of system is that. I could ask you, sketch the step response of this system. What kind of system is that? You have 2 poles exactly on top of each other. It is what? It's a critically damped system. So it's critically damped. So if I ask you, for example, I could ask you, these are 2 systems. On the same figure, plot the step response of these 2. How do you plot them? For the first one, you would show oscillation. For the second one, you show no oscillation. And by the way, this is a faster system. A critically damped system is the fastest possible second order system. Even overdamped is slower than the critically damped. So you get the idea. So you could be asked various questions. I can twist and turn it in many different ways. But if you understand the basic idea of the relationship between location of poles and omega n and zeta, you're all set. You can answer any question I throw at you. You need to know 2 facts. One is that this this distance, if I can get a line in between, this is omega n. That's the first fact you need to know. And the second fact you need to know is that sine of this angle defines zeta. Sine of the angle is zeta, and the distance between origin and the pole is omega n. If you know these two, you can answer many different questions. So you can see for the green, sine of the angle, because angle is pi over 2, sine of it has to be equal to 1. So this is definitely a critical damped system. But that could throw you off a little bit, because for overdamped system, they're also on the real axis, but the difference is that they're distinct. They're two poles as opposed to on top of each other. So what I just said is, if I give you a third case where you had two poles, that's a terrible choice of color. So if you had another pair, this and that, and one was here and the other one was there. Again, this is also a second order system. Two poles, both real, but by now you know it's a overdamped system. It's an overdamped system. So the difference between critically damped and overdamped is they both have two negative and real parts. But one, for the critically damped, they're on top of each other. For overdamped, they're separated from each other. So please take advantage of homework problems and an exam, and come to an exam sample that you have, and come back to this many times and etch it if you could on your brain, so you don't have to even think about it. Okay, so we talked about the transient response and the fact that location of poles on the complex plane will define the response. By the way, these figures, I have a larger version of it. These are impulse responses. You remember impulse responses? They are effective initial conditions, as if you only have some initial conditions and let the system run. So depending on the location of poles, you have various impulse responses. You can see that as we get closer to the origin, the response gets slower. And if you're exactly on the imaginary axis, the response gets oscillatory. And we never had this case, but if only one of the poles are to the right of imaginary axis, only one. If only one of the poles is to the right of imaginary axis, you're dealing with an unstable system. Now, what does an unstable system mean? Unstable system means you give it a limited input, but the output is very large. It could lead to a damage to the rest of the system or self-destructing the system. So it's definitely an unwanted behavior. So stability, my point is, stability also can be determined by location of poles. Even if one of the poles is to the right of the imaginary axis, you have an unstable system. And this is definitely unwanted. The response would blow up if you have an unstable system. So that's what you want to avoid, but you also want to tell if a system is unstable simply by looking at the location. So there are two definitions, as the two slides following each other suggest. One is limited output, limited input leading to unlimited output. That's one definition. And the other one is whether or not a small deviation would cause the system to stay in the neighborhood of deviation or pushes it completely away. And a very simple example to demonstrate this second definition is looking at a pendulum. You remember the pendulum? It was a length at the end. It has mass, and this was angle theta. You remember that this system had two equilibrium positions. One was 0, and the other one was pi. Now, the first one is a stable equilibrium. The system is stable around theta equal to 0. Why? According to this second definition, if you just deviate it a little bit, it goes back to 0. But imagine the other case, where you are around pi, theta equals pi, 180. If you just deviate it a little bit, would it stay around 180? Definitely not. It just flies away and goes to the stable equilibrium. So that's the other definition. And hopefully we'll get to see this example. Why don't we look at it right now? You can see that the poles of this system, you remember we came up with two linearized versions of the differential equation? Do you remember that? Now, if you look at the poles of those two systems, you would see that one of the two poles for the unstable equilibrium is to the right of the imaginary axis. If you have your notes, go back and take a look. So I believe it was 1/2 ml squared theta double dot plus b theta dot plus mg L theta equals t. This was for the stable around theta equal to 0, and for unstable was minus mg L theta equals t. And the rest was similar. That's what I remember. If you could just verify that by looking at your notes. So when you turn this into a transfer function, by now you know that what is on the left-hand side will end up being the denominator of the transfer function. So in your transfer function, for one case you have 1 over 1/2 ml squared s squared plus bs plus mgl, and for the next one you have again the same denominator, but you have minus mgl as the coefficient of s to power 0. And if you apply the quadratic formula, so a is 1/2 ml squared, b happen to be b in this case, and c either is plus mgl or minus mgl. Plus mgl or minus mgl. If you apply the quadratic formula, you can see that this would give you a positive real. So it's minus b plus minus b squared minus 4 times ac. So if c is negative, your minus 4ac basically becomes positive. So you push one of the two poles to the right of the imaginary axis. So please continue this. So what I'm asking you to do is show that the poles of both models, recognizing that they're both representing the same system. One is the model of the system around theta equals 0. The other one is model of the system around theta equals pi. And that's how we linearize it. We had to pick our neighborhood, if you remember. So this first model is about theta equals 0, and this is about theta equals pi. So stable, unstable. So if we do the calculation correctly, for the unstable system, we will find a pole that has a real but positive real number and that's an indication of an unstable system. So that's what I'm asking you to do, and we can discuss it if you have any questions next time. Okay, so let's look at one more time. You already know, but let's look at one more time at finding a steady state response of systems. This is a review because we want to look at various models and how to find a steady state response of various models. If you have differential equations, it's fairly straightforward. You drop all the dot terms, and what is left will determine your steady state response. So, for example, if u is 1, if u is 1, which indicates unit step, for this differential equation, you can see what is left is omega n squared x, steady state is equal to 1, which then immediately follows that x steady state is 1 over omega n squared from this differential equation, whatever this differential equation is representing. So fairly straightforward. Why don't we now apply this to a model that we developed? If you remember, for a system that has a source of voltage, a resistor, and an inductor connected in series, we found the equation. Didn't we find the equation? Do you guys remember the equation that we found for a system with a source of voltage, a resistor, and an inductor? If I remember it correctly, this was the system, the equation we had was this. It was L Q double dot, was it L Q double dot plus, now let's do it from scratch so we don't have to guess. So if you apply, let me add a slide so we can look at it together. So the system that we are trying to model is made of source of a voltage, a resistor, and an inductor in series. So R and L. So if you write Kirchhoff's law, you would have L di over dt plus Ri is equal to V. So the question is, if V is a unit step, so if V is 1 volt, what would be I steady state? What is I steady state? Is 1 over R, just by dropping the term with derivative. Now let's look at this mechanical system. Let's apply the same concept to this mechanical system. We found the model for this system where x1 measures how much deflection we have from equilibrium in mass 1, and x2 measures how much deflection we have from equilibrium of mass 2. When you draw a free body diagram and write Newton's second law, you arrive at these two differential equations, and that's expected. They're two second-order systems, so two differential equations. So this is the question. What is the steady state position of mass 1 in response to a unit step force input? I'll give you a minute to calculate that. So if F is 1, unit step, we are asking x1 steady state. What is it equal to? What is x1 steady state equal to? What is the answer? Still working? So you have to start from where F is present, which is the second equation, right? So if you set F equal to 1 in the second equation and drop every term that has any dot or double dot in it, what do you get? You get K2 x2 steady state minus x1 steady state is equal to 1. Do you agree? So put 1 for f and drop every term that has a dot or double dot. What is left is K2 times x2 steady state minus x1 steady state has to be equal to 1. Do we agree on that? Okay, now let's go to equation 1. The equation 1 do the same thing. Drop every term that has dot or double dot. And what you have in that equation 2 is what? You have, if you have minus K1 x1 steady state plus K2 times x2 steady state minus x1 steady state equals 0. Okay? So where do you go from here? What can we do? Basically, understand that K2 times x2 minus x1 steady state is 1 from the top equation. So if you drop this and make it equal to 1, you can see that x1 steady state is simply 1 over K1. And nothing else affects the steady state value of x1. It's simply 1 over K1. Why? Because K2 times x2 steady state minus x1 steady state is 1. Okay? Now, here's your next question. What is x2 steady state? Where do you look to find x2 steady state? So right here, you have a relationship between x2 steady state and x1 steady state in this equation. So if you substitute for x1 steady state as 1 over K1, you'll get your x2 steady state. So let's rewrite this. So according to this equation, x2 steady state is equal to 1 over K2 plus x1 steady state. Can you see that? That x2 steady state, if you rewrite this equation by dividing both sides by k2, you get 1 over k2, and then if you move x1 steady state, you get x2 steady state. Now if you substitute for x2 steady state, then x2 steady state becomes 1 over k2 plus value of x1 steady state, which is 1 over K1. Isn't that interesting? That steady state position of mass 1, it only depends on value of K1. But steady state position of mass 2 depends on both K1 and K2. You ready for more fun? We talked about a final value theorem a couple of times, and essentially we said if you want to find the step response of a transfer function, just drop all values of s equal to 0. But now let's look at it in a more general form. Final value theorem basically gives you value of a time function if you have its Laplace function. So if Laplace function of f of t is capital F of s, and you have f of s but you don't have f of t. So if you have access to f of s but you don't know what f of t is, and you really want to know the steady state value of f of t, So if everything, once time passes enough and you reach steady state, what is the value of a steady state of f of t? The theorem says steady state value, basically this tells you steady state value of f of t is simply limit of s times f of s when f of s is Laplace transform of f of t when s goes to 0. Okay? So that's the basic theorem. So if you're dealing with this transfer function, and remember, transfer function is this. So g of s is really output y of s over input u of s, right? And let's say, and you know this is, in this case, k dc over ts plus 1. And you're really interested in y steady state in time domain. Remember, you're after response in time domain in steady state. So basically this tells you if you're after y steady state, what you need to do is first of all find y of s. Y of s, according to this, is equal to u of s multiplied by the transfer function, which is k dc over ts plus 1. So this is your y of s. Now, according to final value theorem, what you need to do is to take y of s and pre-multiply it by ns and let s go to 0. That's what you need to do. Now, if you look at the table of Laplace transform, for any function, there is a Laplace transform. Now, for unit step, the Laplace transform happens to be 1 over s. So if u is 1 in time domain, its Laplace transform is 1 over s. So if u of s is 1 over s, that 1 over s with the s that you multiply with, according to theorem, cancel each other. That's why it's enough to just drop s equal to 0 in the transfer function to get the steady state response to a unit step input. I'll write it down so you have it somewhere. So what I said is, let me add a slide here. So if u of t is 1, u of s would be 1 over s. This is coming from the table, or you can take the integral and find it, but it's tabulated. So that's why when you are after y steady state, according to theorem, you have to pre-multiply by s, and then multiply by u of s, which is 1 over s, and then multiply it by g of s, and let s go to 0. Now, because s and s cancel each other, what is left is g of s when s goes to 0. So in order to find steady state response to a unit step, it's enough to drop s equal to 0, which is what we have been doing so far. But now you have a more general tool. So you can calculate steady state response, for example, if you have a unit impulse input, or a ramp input, or a sinusoidal input. So it's different different function for different input in s. So this is another example. So if g of s is 3 times s plus 2 over s times s squared plus 2s plus 10. What order system is this, by the way? What is the order of the system? It's a third order system. Very good. So let's say we want to find g of t when in steady state. So what you need to do is you need to pre-multiply this by s and let s go to 0. So if you multiply this by s and let s go to 0, you find 0.6 as the value of g of t. Now let me give you another example. Find so this is y of s over u of s. I'm now asking you a different question. Find y steady state if u of t is 1, which implies immediately that u of s is 1 over s. So I'll give you a minute to calculate y steady state if u of t is 1 for this system. So according to theorem, y steady state is s times u of s times y over u of s. Essentially, it's equal to s times y of s when s goes to 0. Now, if you substitute, s is s, u of s would be 1 over s for unit step, and the transfer function is what you have over there. So I'm just going to write it as g of s, and let s go to 0. So what is that number? That number is? So these two s will cancel each other, s and 1 over s. So what is left is to substitute s equal to 0 here. So if you did that, what will you get? So from the numerator, you get what? What do you get from the numerator if you set s equal to 0? You get 6. From the denominator, what do you get? Denominator, you get? You get 0. So this tells you that, this tells you what? It tells you that y does not have a steady state number. So it basically keeps growing. If you let this system run, the y value keeps increasing, so it doesn't have a steady state value. So it basically goes to infinity. So y steady state, in this case, goes to infinity, which means does not have a steady state value. So the response keeps increasing. Okay? So these are two examples. I'm going to leave them for you to solve. You already have these two transfer functions from previous examples that we solved. You have g1 of s, which is the transfer function between f and x1, and you have g2 of s, which is the transfer function between f and x2. So you have those two. So what I'm asking you to do is to find x1 steady state and x2 steady state in response to a unit step input. And by the way, you already know the answer. In the previous example that we solved, we found x1 steady state and we found x2 steady state from the differential equation. Now I'm asking you to apply the final value theorem and verify that you get the exact same answer. Is it clear? So I'm going to leave this for you to solve. And we'll start next time by trying to find steady state response from the last way of modeling, which is the state space model. So I'm going to stop here. And you will expect a quiz coming up. I'll let you know as soon as I host a quiz. Thank you.